Today will be our first lesson for set theory on connecting words. So make sure you're following along in the notes and taking down any important information. Now, set theory is a great unit for Math 30-2. I always love teaching this unit because it's tangible for all students, even those of you who don't particularly love math. So we're going to start with some of the basics today and then build on it throughout the unit. And it's going to feel a little weird at first. It might even feel like you're back in English class, but hang with me as we get through some of these definitions. So the first thing you need to know is what a statement is. Now, a statement is just a sentence that has a truth value. So a truth value means that it can be either true or false. A sentence that may be judged true or false by another is not considered a statement. It is an opinion. So let's go through some examples. The first line here says the city of Vancouver is in the province of British Columbia. So not only is this a statement, but it is also a true statement. So remember, a statement just has a truth value, and yes, this happens to be true. Okay, the next one says the city of Vancouver is on the planet Mars. So although this is a statement, it is a false statement because we know Vancouver is not on Mars. The next one says Vancouver is the best place in the world to live. So this is what we call an opinion. So it's important to note that opinions will not have a truth value. So you're not going to tell me that it's true or false. It's just an opinion. So on your assignment, it'll ask you for which ones are statements and which ones are not, and only assign the statements with truth values. Okay, the next one, the last one here says, how do you get to Vancouver? This is also not a statement, it's a question because it does not have a truth value. So let's try some examples. The first example here says, determine whether each of the following is a statement. For each statement, list its truth value. Okay, first one. The number 4 is a prime number. So the first thing that I notice is that, yeah, this is definitely a statement. Now it's whether it's true. So I'm just going to jump ahead a couple pages to show you the definition of a prime number. So if you see here, I've got the definitions down for you just a little bit later, a prime number. So if you don't know what a prime number is, it is a number that is only divisible by 1 and itself. So 2, 3, 5, 7, 11, these are all prime numbers. For example, 11 doesn't divide by any numbers other than 1 and itself. So you could continue this list. 13 would be next, followed by 17 and 19. And I notice right away that 4 is not on this list. So going back to this example, it said 4 is a prime number. This is false. The reason it is false is because 4 also divides by 2, not just 1 in itself. And just so you are aware, if it's not a prime number, it is the opposite. So the opposite of this statement, which we will be talking about as well, would be the number 4 is a composite. So composite means it divides by more than 1. All right, next example. Driving in a car is the best mode of transportation. So although you might think so, this is not a statement. This is an opinion. And then remember that opinions are not assigned truth values. Okay, the next one. If you double an odd integer, you get an even integer. So I do notice that this is definitely a statement. Now the question is it true? So let's just reread it. Double an odd integer. So remember, an odd integer is a number that ends in 1, 3, 5, 7, or 9. So if I double an odd integer, I'll get an even integer. So I'm just going to try it. 3 is odd. I'm going to double it. I get 6. 11 is odd. I'm going to double it. I get 22. So yes, this is a true. If I double an odd integer, I will get an even integer. And also note that this works for negative numbers. If I double, say, -5, I will get -10, and that is an even integer. Okay, so now that we know what statements are, we need to know what the negations are. So negations are essentially the opposite of our original statement. So the negation of a statement is the exact opposite of the statement. Typically, we're going to use the word not to form a negation of a statement. Negation of a statement, so here's our example. The city of Vancouver is in the province of Alberta, just like the one we saw above, is the city of Vancouver is not in the province of Alberta. So if we add that word not into our sentence, we will have the negation of the statement. Now, later in Math 30-2, in the next couple of lessons, we'll also talk about this being called the complement. So I am going to write that word down. The complement is the exact opposite. And then this piece here is very important. It says a negation must always have the opposite truth value of the original statement. So this will really help us when we are writing our negations and where we put that word not. Okay, our next example is a multiple choice question. It says a student made the following false statement. All triangles are isosceles. So just so you guys know, isosceles triangles mean, oh, here's my line, mean that two of the sides are the same and one side is. So it says all triangles are isosceles. The first thing I know about that statement is that it is false. We have other types of triangles as well. We have equilateral triangles, which means all sides are the same. And we also have scalene, which means all sides are different. Oh, I forgot to put a double line. Okay, so two sides are the same, one is different for an isosceles triangle. So it says, which of the following is the negation? So remember that when we're talking about that negation, it has to have the opposite truth value. So we are looking for one that has the truth value of true. So all triangles are not isosceles. I noticed right away that that word not has been added. However, this is still a false statement because we still have isosceles triangles. So that one cannot be the negation. Then we read B, not all triangles are isosceles. That's a true statement. We still have isosceles triangles, but not all of them. So this is going to be our answer. Check C, it says all triangles are scalene or equilateral. Once again, that's false because we need to have isosceles triangles. So C is not correct, it is false. So therefore it cannot be the negation. Okay, next example says write the negations of the following statements. It is 20 degrees outside. So the negation is the exact opposite. It is not 20 degrees. Add that word not in there and it has the opposite truth value. Okay, the next one says, it is not Saturday today. Well, that's true. However, we need to come up with the negation. So something that has a false truth value. And not only can you add the word not, you can take it out. So it is Saturday today is the negation of this statement. Okay, moving on to compound statements. So a compound statement is formed by combining two statements, like we learned before, like the statements we learned previously. However, we're going to combine them with either the word and or. So these two words have different meaning, and that's what we are going to focus in next. So first, let's look at the word and. So when we get into set theory, we will be using this symbol here. It's just kind of like a large upside down U or a large lowercase n to represent the word and it also means the intersection. So this is called the conjunction of two statements can be formed using the word and. So basically we're taking two statements and using the word and in between them. So the conjunction is true only if both the original statements are true, otherwise it is false. So let's go through what this actually means, and we're going to use two statements. Our statements are blue is a color and ice is a solid. So if we look at the first one, it says blue is a color, and we know that's true. So that has a true for its truth value. Okay, and then the second one, ice is a solid. This is also true. So because both of them are true, the entire statement is going to be true. The next one says that wet is a color. Now that is false, so I will underline it in pink. So wet is a color and ice is a solid. So ice is a solid, that's still true. But because one of them is false, the whole statement is now going to be false. And then our last example says wet is a color, which is false, as we talked about before, and ice is a liquid, also false. So therefore, the whole statement is false. So when we're using the word and, both statements have to be true in order for the compound or statement to be true. So we'll get into using some more numbers for these things, but for now, both statements have to be true in order for the whole statement. So this is different from using the word or, because when we use the word or, the only time it's going to be false is if both statements are going to be false. So as long as one of the statements is true, then the whole statement is going to be true. So that's what this part here says. It's going to be true if either the first statement is true, the second statement is true, or both statements are true. So we just need to have both of them false to be false overall. So in order to answer the next couple questions, we're going to need to know some definitions. So take a look through these. They're mainly sets of numbers. We've got the natural numbers, which are our counting numbers. So 1, 2, 3, 4, etc. Those are the natural. If we take our counting numbers and add in 0, we get what's called whole numbers. So 0, 1, 2, 3, all the way up to, all the numbers. And then integers, one step further, now it's our whole numbers, but it's also any negative whole numbers. So -3, -2, -1, 0, 1, 2, 3, but no decimals are involved. Okay, multiples are what we get when we skip count. So if I say to skip count by 3 and you go 3, 6, 9, 12, 15, those are all multiples of 3. Factors are the numbers that you multiply together to give you the other numbers. So when I talk about the factors of 15, 1 times 15 multiplies to 15, and 3 times 5 multiplied to 15. So therefore, all of those numbers are going to be factors of 15. And then we already talked about prime numbers, but a number only divisible by 1 in itself. And just a special note on this, that 1 itself is not prime. 1 is kind of a anomaly. It's not prime, it's not composite, it just doesn't satisfy any of those groups, but it is not going to be classified as a prime number. Okay, so now we are going to try some examples here. So example number 1 here says, consider the natural numbers x that are less than or equal to 15. List the numbers which satisfy each of the following conditions. So in order to answer this question, I'm going to start with all of the numbers that we're allowed to use. So it says the numbers x that are less than or equal to 15. So natural numbers means 0 is not included. So we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, wait. Less than or equal to 15. Oh, so I can include 15 because it says less than or equal to. 16 is not going to be included. So these are the numbers that we get to choose from. So the first one says, out of these numbers, which ones are prime? So I just mentioned the fact that 1 is not prime, but 2 is, 3 is, 5 is prime, 7, 11, 13, and that's it. I can't go higher than 13. So those are going to be the ones where x is. Oh, I put that in the wrong spot. Sorry about that. I read the wrong one. That's B. Give me a second to make sure you erase that. The one before that said x is odd. So for x is odd, those are the numbers that don't divide by 2. 1, 3, 5, 7, 9, 11, 13, and 15 is also odd. Okay, sorry about that. So now we've got x is odd, x is prime. So here's where we're going to be using the word and the word or. So the first one says x is odd and x is prime. So in order to complete this, it has to be true for both of them. So we are looking for numbers that are in both of those sets. So I'm looking through all of them, and I see that 3 is in both of those sets. I see that 5 is in both of those groups. I see 11 is in both of them, and I see 13. It has to be in both of those groups in order to be included. I think I missed one. I think I missed 7. So just looking, and you can even use a highlighter. That's what I like to do. My highlighter function's not working the best right now though, so highlight the ones that are in both of the sets. Okay, so that is different from the word or. So the next one says x is odd or x is prime. So now we combine both of those lists because 1 is odd, so it goes on my list. 2 is prime, so it goes on my list. 3, 5, 7, 9, make sure I don't miss any, 11, 13, and 15. So it's essentially taking both of my lists and smushing them into one list. Okay, now moving on to the word factor and multiples. So E says X is a factor of 3 or 5 or 7. So remember that factor means they multiply to those numbers. So the factors of 3, I'll just list them above, are 1 and 3. The factors of 5 are 1 and 5 because they multiply to 5. And then the factors of 7 are just 1 and 7. So because that word or is being used, 3 or 5 or 7, then when we go to make our list, we're going to combine all of those. We don't have to put 1 down more than once, just one time for 1. 3, 5, oh, that's supposed to be a comma. 3, 5, and 7. Okay, lovely. And then the next one says the same thing. X is a factor of 3 and 5 and 7, but notice that word and. So now it has to be in all of those groups. So the only number that's in all of those groups is the 1. All right, the next one I'm going to make some writing on the side to help me out with it because we need to know the multiples. So multiples of 3 are going to be 3, 6, 9, 12, and 15. So I get those just by skip counting. The multiples of 5 are going to be 5, 10, and 15. And then the multiples of 7 that are within my list are just 7 and 4. So this will help me when I'm answering my question. So the first one says X is a multiple of 3 or 5 or 7. So we're using that word or. So remember when we're using the word or, it can be any of those. So we're going to take all of those numbers from our list and we are going to combine them into one list. So 3, 5, 6, and I am attempting to write them in ascending order, so hopefully I can not miss one. Okay, so I have 3, 5, 6, 7, 9, 10, 12, 14, 15. Okay, then when I use the word and, now it has to be in all of those sets. Now, funnily enough, I don't see any numbers that are in all of those sets, so this one is going to be none. There are no numbers that add or that satisfy these conditions. So I'll put that down, and then next class we'll be talking about some of these in a little bit more detail. But if there's none, we would actually call this what's called the empty set. So that is a circle with a line through it. So we'll talk more about that. But there are no numbers that satisfy this because there's no numbers that are in all of those groups.